Can I screen?
Yes, Daniel, we can see your skin.
But before, just to confirm, did you send out the link? Okay, yes. Okay, yeah, I remember you've not sent it out, but you sent out the link for week 6, right?
Yeah. Which other link are you talking about?
No, I just mean the GitHub, like the normal link you send GitHub, like resources for week 6. Is not
Yeah, that one I sent out yesterday.
okay, cool.
Sure.
All right. We're gonna start. Not sure how to. I need to stop sharing this. Not. Stop sharing. This full screen. So guys, I'm trying to. Oh, okay, I see the number is increasing now. Great. Okay, good morning, everyone. It's time. We are in week 6 of the BRICS Idea Data Analytics program, and I'm going to say congratulations for staying with us thus far because this is not easy. I understand many of you taking this kind of course for the first time, and it is challenging. It is not easy to navigate your personal activities as well as going through programming and the diverse topic we've been covering, from programming with Python itself to data analytics to things in astronomy, where we talked about data sources as well as time series analysis, which happened last week. So this week we'll be looking at machine learning. So this is not a promise that everything about machine learning will be taught here, because this course is not specifically for machine learning. But then hopefully in the future we'll probably run a course that is focused more on machine learning. But this is just to give you introductory concepts on what machine learning is for those who don't know, or for those who know, to also see how it is applicable in sciences, astronomy in particular. This very lecture is going to assume that you also have programming skills to an extent, and you also understand a bit of the concept of data and whatnot. So let's get started. So what is machine learning? I think what is very common today is that over the years is the development of computers, and it became a household item. What has been happening is that everybody is going through some form of computing infrastructure, whether as a personal computer, a desktop computer in your workplace or at home, or a laptop, or even your mobile phone. And what it means is that you have infrastructure that processes information at all time. And at the end of the day, what is this information? The information is data. Either it is collecting data or it is interpreting data. But the only reason why you're able to use your computer is because it performs processing of information. And this information are data of different sorts, logs, telemetry, the tabular data sets and whatnot, text, images, graphics. So And over the years, the development of computer keeps, increasing incrementally in terms of computational efficiency, be it the hardware, be it the processing RAM, or be it the storage facility or the storage infrastructure. And what it means is that we now have tons of data. Today, if you go to YouTube, you'll see that there are plenty of videos. You can learn 1,001 things, anything you can think of. You go to TikTok. Same thing is also applicable in other fields, because that is entertainment. You talk about science. Every day people are collecting data. Where are you storing this data? What are you going to use this data for? So these are part of the things that gave idea to machine learning, is that we are processing enormous data. How can we process this data? What can we learn from this data over time? And how can we use some of the things that we have learned from this data to make improvements, to predict not the future, but to predict new realities or maybe events that is just happening or might happen. That is, if you're like something that might happen in the future, you call it forecasting. So the idea of machine learning did not just come out of the blue. It's something that is also that's happened as a result of the development in computer science, computing infrastructure, and the tons of data that we've been able to develop. So over the last few weeks, we've been talking about astronomy, right? We've talked about science, we've talked about programming, we've talked about analytics. And at the end of the day, we're now looking at insights. We're now looking at predictive analytics. So what it means is we need to also hone ourselves with the skills that enable us to see how we can be able to manage this data or design or produce meaningful information from the data that we've amassed. 2 weeks ago, you did the lecture was about astronomy data sources. You saw there are multiples of ways you can collect data from cloud, from data centers like Vizia, storage systems, Vizia, and many other places. And there are tons of data there in terabytes, not even in gigabytes. And you need to process this. Today, the bandwidth, internet bandwidth is also very fast. It's coming like faster compared to what it used to be 5-10 years ago. At the same time, your processing system is also large that you can process huge amount of data compared to the kind of computers that used to exist 10-15 years ago or 20 years ago. So now, at the same time, people are also developing algorithms through which these data can be understood or learned from. So generally, like I said, development of data led to the idea of how can we learn from this? Because remember, the idea is learning. How can we learn from these tons of data we have developed or that we now have in our repository? That is where the idea of learning, came into the system. So people have been thinking about other scientific learning, which you have done in the course of your data analytics, introduction to statistics. You have done a bit of that where you are looking at the distribution of a data set, tabular data sets, you're looking at the distribution, you're also looking at the things like the variance, the mean, and many other statistical things, hypothesis testing, trying to understand what is changing in the data and all that, what is relevant and what is not relevant. That is you learning from the data. But now we're looking at how we can design computers to now do the learning themselves instead of humans doing the learning. And this is where the field of artificial intelligence comes in. And that is why today a lot of you have been hearing the buzzword AI, it's happening, but AI did not happen overnight. The development of AI has been in the works since the early 90s something, when I mean 1900s. So it's not something that just happened a few months ago or a few years ago. So machine learning is a way of computers learning from data without being programmed. So you have done the parts where you sit down, you write your code, you see what you can do to play around data to find something from it. But machine learning is where you're now trying to give computers the ability to do this learning themselves. And how do they do this? They do this through a bit of algorithms, a bit of models, a bit of codes that computers themselves can understand. And but that's it. Some of them is also something that you have played with, especially if you've done something in high school or even in your early undergraduate days where you do something like regression. So regression is also one of the simple ways of machine learning where you're trying to learn from data. You understand? But here, why you do it manually, computers can also use that technique to also learn from data. So we'll have a couple of examples today, like when you talk about machine learning. I know the easiest one people usually say is maybe comparing, here's an object recognition example where you have a card. And then you pass this data to the computer over time, to the algorithm or the model that you're training over time. They start learning the shape, the variation, the pixels. So they start understanding the pixels to understand that, oh, maybe this is the head, this is the eyes, this is the nose, this is the shape of the cat. So, and this is applicable. So over time, it learns this. It's able to now differentiate whether something is a cat or not a cat. It's able to differentiate whether something is a dog or not a dog. And it goes from there. So it could be anything. It could be other forms of data. Maybe in your case where you're doing astronomy and then you're trying to see if something is an AGN, is a quasar, is a star, and many others. It could be maybe what type of star is this? It could be maybe a binary star, it could be a single star, it could be a late type star, it could be a white dwarf. So, and many more, not just in astronomy, in other sciences, maybe in the case of atmospheric science, it could be, or earth science, it could be, which region is terrestrial, which region is mangrove, which region is an urban area, which region is a desert, which is an ocean, what's the atmosphere. So these are some of the things that AI machine learning can help you do. And just giving you a bit of the concept is that you have a data. A majority of the time in machine learning, you have data that has been prepared. So you need to prepare the data, and then this data has some features. Now, this data itself comprises of features. What are the features? Properties. For example, as a human being, what is your property? What can you, when you say, oh, what are humans? You can probably say, oh, maybe race, maybe age, maybe gender, maybe height, maybe weight, maybe body mass index, and the rest of them. So these are features. Now, these features can also be ascribed to other things, both living and non-living things, including the data that you pass into your system. Now, another example is looking at the Astro data sources lecture. You could see that when you fetch a data from Visia, you fetch a catalog, a part of a catalog from Visia, you notice that the table has so many features. You understand? Maybe things like different magnitude filters representing the observations that was done, the coordinates where the positions of the object is, the other properties like maybe things like proper motion, absolute magnitude, and many other things you can think of. So now, this is the same way you have these features. This is what your data is, because when we talk about data is more like set of features that you have prepared, set of properties, the information that you have prepared in a way that the machine learning can understand. And then after we do this, you pass this data to a set of algorithm that we usually call an estimator. Now, this estimator takes this data. We call it training data sets. And then the data set also has some sort of labels. Maybe this is the property of this data. I have this data, and then this is the property. Maybe you say, a good example could be maybe fruits. You could say oranges, mango, pawpaw, and the rest of them, and each of them have their own features. And then you label it and say this features has this is the class it belongs to, or whatnot. It could be that. It could also be a case where it's just like you assigning number, like student. What are the properties of people who perform, of students in class, to show whether they pass or fail a course? Maybe the reading time, the sleep well, study time, work rate, and the rest of them, family background, demographics. And you can say this is the average score the student can get in a test or in an exam. Now, when you pass this to the model, you train it over time. Now, the reason why you need to train it is that you don't just take the data and give it and then it understands. So you need to keep passing it over time, like repetitively, just like you learn. For example, you taking this course, after the lecture, if you don't go back to the resources to go and look through it over and over again, you will not be able to understand the full concept. So this same thing is done to a computer or to a machine learning model so that it can learn. And then at the end of the day, you have some, it learns to a great extent, and then you can see how much it has learned. And then in that case, this is where you do things like prediction to say, okay, oh, I have this data that I've labeled. How much of it did it learn very well and all that? So so that's just a bit of this. So I need to run very fast. So we have types of learning, different types of machine learning. We have supervised learning, we have unsupervised learning. Now, supervised learning is a case where you have your input and outputs well prepared and passed to the data to say, hey, machine learning model, I have this data set, this is the properties, and this is the value. Please go through it over time, learn from it, and please develop a model that I can learn from it very well, such that I can reuse this model to do what? To make predictions. So that is a case where you have two sets of data. You have one data actually, but it is well prepared such that it has the features and the labels, or what you might call inputs and outputs, right? Now, for supervised machine learning, they are mostly of two types. You have the classification and regression problems in supervised machine learning. So classification is a case where you're dealing with, when you are dealing with things that are classes or like properties, things like, okay, example could be a cancer. Especially those in the health sciences, maybe you want to predict things like cancer, whether somebody has maybe a particular type of cancer, whether someone has a cancer or doesn't have a cancer, or a case whereby in other health sciences could be like pneumonia, asthma, COVID, and bronchitis, and the rest of them. It could also be a case in astronomy, maybe where you have different types of galaxies, and then you're trying to look at, based on the shape of this galaxy, what type of galaxy is this? Is it a lenticular galaxy? Is it a spiral galaxy? And so is it an irregular galaxy, or in the form of a star? Is it a massive star?
Can we? Can we? क्या
I think it froze. Just wait. Daniel, I think there was a network problem. You'll have to.
Apologies. Yeah, I think I'm noticing
It
it
suddenly
now.
froze.
Okay.
So just repeat
Sorry,
the
we are
network.
not hearing.
Can you hear me now?
Yeah,
Yeah, now you're good. Now you're good.
yeah, good.
Okay, good. So where did I stop?
I think just a minute ago. A minute, 1 minute.
Oh, really? Apologies. So I was talking about supervised machine learning. So where you have, we have classification and regression problem. And the classification problem oftentimes has to deal with things that you're able to label or classify. A good example could be a galaxy, where you have maybe, say, irregular galaxy, elliptical galaxy, spiral galaxy. It could be a form of, maybe you're talking about other types of objects like compact object, extended objects, AGNs, quasars, stars. It could also be other things like maybe you are looking at molecular clouds, those who study star formation and say, oh, this is a massive star formation region, this is a low mass star forming region, and the rest of them. So it could be of this nature. Then on the other hand, you have things like regression, where it could be like, oh, I'm looking at the property of an object. Maybe I'm looking at things like, especially those in cosmology or even extragalactic physics, where you're looking at regression. Oh, sorry, not regression. Redshift, like, oh, how far is this object away? So these things are numerical values. It could also be of many cases. Maybe you're trying to predict the weight of an object, or you're trying to predict maybe, say, things like temperature. example, oh, what's the temperature now? I could say, what is the temperature now? Or let's look at the weather. You can say, oh, the temperature is, say, 18.5 degrees Celsius, right? So these things are continuous. On the other hand, classification in the terms of weather could be, is it hot or cold? You understand? So is it sunny or not sunny? So things that you can classify. These are a bit of the examples. Then for unsupervised learning, you also have a case. This is a case where you also have a data set that has features, but then you have the features, but you do not necessarily have the labels. And in that case, you pass these features to the data and say, please, I want you to look at this data, and then I want you to figure out something from it. Majority of the time, in these cases, you have there are two common cases where you have the most popular one anyway is clustering. So clustering is where maybe you have a set of data. You give and say, how can you learn from this data? Can you find features that are quite unique or similar? You understand? And it can be able to do this. So because of time, let's also run. So this is an example of classification. You can see, oh, these are two distinct objects. I think that, sorry, I'm very, very bad with colors, but you can easily distinguish this and see that this is a set of what distinct objects. And then on the other hand, for things like regression, you have, like I said, continuous variables. You have just like numbers where because you can't classify them. Otherwise, you're going to have limitless number of labels. And so this is more like an example, maybe things like age or temperature of a day. And then for unsupervised learning, you have an example of clustering where maybe based on the features of a data set, things can be, maybe sets of data that are of similar characteristics can be clustered together distantly. For example, you can see this, you can see this, you can see this, you can see this. So they are bounded within a region based on their properties. And then, so like I said before, in supervised learning, you need to train your data. You have your data, you prepare your data, you need to train the data, and then you need to, after training the data, you need to also have a set of tests that you need in order to do what? To confirm that your model is learning. So like I said before, you have your features. This is just an example, and there's maybe labels, and then you try and see if it learns. So anyway, yeah, so this is just giving you a set of examples like, oh, we've trained this data. Okay, say this is a training data with labels, and then we're trying to see if it can learn something in terms of maybe translation. And then we have this case whereby we now have some set of data to see if it's able to, if it's learning, and how much accuracy is it learning? How far is it learning this? Is it learning very well, or is it poorly learning? So these are a set of things that you need to do. So we also have another type of machine learning called reinforcement learning. So reinforcement learning is where I think like follows a game theory where you also have allow the computer to explore the data set and see how much of it can learn by itself and is rewarded based on how much it's able to learn. So this is where agentic systems play out. But like I said, this area is not usually talked a lot in AIs or in most machine learning courses, but this is also a part of machine learning. So it keeps learning by trial and error. And to be honest with you, a lot of the LLMs that you are hearing today, things like ChatGPT, things like Google Gemini, they released a new version yesterday. And then things like Anthropic Cloud, you have other ones like Meta, Llama, and the rest of them. They also follow this technique, reinforcement learning technique. So reinforcement learning technique is also very useful in robotics, where you're also trying to program set of mechanical systems to see how much they can perform certain tasks and all that. So but now, even in the era of AI, we're moving to agentic systems. But reinforcement learning is not part of what we're going to discuss anyway. But if you want to learn more about it, there are a couple of courses. I think Harvard has one on, I think Harvard or MIT, that is freely available on YouTube. on reinforcement learning. Hugging Face also has their own course on reinforcement learning. So we've talked about data sets. Over time, we have been playing with data since the beginning of this course. So we have sets of data sets when you have attributes and their values. You have things like categories, you have ordinal, you have numeric. Some of these things is some of these things you have already encountered in the course of your program, where you see different kinds of data. Even in Python, you know how to represent these things, maybe in a list, in a NumPy, in an array using NumPy, or maybe if you have a lot of them, you can also represent them. Maybe if you want to see them in a tabular form, you can represent them in a pandas data frame. You always notice that these things are different. Or maybe you can see floats, you can see integers, you can see objects. Most times objects in pandas are also strings or lists or arrays. So I'm not going to spend a lot of time here. This note, so here's an example. These are examples of data sets, handwritten data sets. So some of you may have done something on machine learning in the past. You may have encountered this handwritten, especially if you're doing things around object detection or object classification. You will see a lot of these examples. I'm not going to spend a lot of time on this because I need to move on to the hands-on, because I think I only have less than 30 minutes to do something here. And then, but this note is freely available in the repo, but I think I've given you some concepts. So now I'm going to stop sharing my screen, and then I'm going to move over to the hands-on side, because I think I need to also, that's also one area that I want us to focus more on today, before Nigel and Priya will come in. Please confirm that you can see my screen. Okay. So if you can see my screen, this is the week 6 repo. In this week 6 repo, we have series of notebooks, about 5 notebooks currently. We also have series of text, PDF, to help guide you on resources. So the slide I just finished sharing now is from Escape School, one of the data science program school that was organized sometime in 2022. It is very, very rich. So that is it here. So you can, it's also very easy. That's why I shared it with you. It contains a lot of information that is not so complex that you can easily understand. Sometimes it's always good to start with the basics. And then we also have the one by Najam. This is more focused on astronomy. Priya and Najam is going to go through this one later. I just want to emphasize this because I know most times we share notebooks and people don't know that there are also PDFs that they can also consume. It can also make your life easier. We also have, this one tells you more about classification, validation, and optimization of machine learning models. You may not, it's also important for you to read through and understand the concepts. Some of these things we already have an example in the notebook. And then we also have this one, validation optimization slide. So this also goes you through about how to optimize, how to validate and optimize your machine learning models for regression. So you see, one is for classification, one is for regression. For the remaining part of this course, program will be dealing on regression and classification. So now I'm back to the notebooks, the one you are used to. Let's talk about the first one here. In the first notebook, you are not supposed to basically run anything. What we did here was to show you more, give you a bit of the concept of machine learning and what you need to understand. Why machine learning is relevant in astronomy. So if you know that astronomy is a field that is already produced tons of data every day, every night, you have telescopes all over the world pointing their observatories all over the world pointing their telescopes in the sky in different wavelengths, either in space or on ground. So what it means is that they are collecting data, and this data is not being collected and thrown away. It is stored somewhere in a repository or in an archive. So you can see that there are tons of data that needs to be mined. And if you mine this data, What are you going to use it for? You can use it for many things. You can use it for science discovery. A good example is Visia. You see that if you go back to Visia, you see that there are tons of data that have been there since over 10, 20 years, even before some of us were born. They are there in Visia. But somebody can still use the data from there tomorrow to make a discovery. So that is the essence of having these archives and repositories. So because it's important that we tie these things together and see how relevant they are. For example, if you're a student, you are working on a research today, after you're done, make sure you keep your research work and data somewhere because somebody might find it useful tomorrow. So that is why, so this is where machine learning is relevant. We have tons of telescopes, we have data everywhere. We have telescopes. Even now, there are still projects that are currently ongoing, like the LSST first light will be celebrated, I think, next week, Monday. So it's going to be the largest transient discovery instrument ever in the history of mankind. What it means is that it's going to triple the current facilities that you have for transient discovery. Now, these things are there, and we need them. We need this data set, and we need machine learning to be able to easily analyze this data for us, learn some things, or understand pattern recognition, because sometimes there are some things that are like anomalies that might happen, that you might see in data, and over time, if the data is too much, you may not be able to look through it, but because of the computing speed of computers, they can easily do this. So I've already talked about these things in the slide, the machine learning types. Here focus more on supervised and unsupervised machine learning, and then a few examples, and give you some common use cases in astronomy: object detection in images, supernova typing, galaxy morphology, regression, photometric redshift, stellar parameter estimation, star clustering, looking at maybe things like star clusters. Some of these things is what you can actually use Gaia data to do. Galaxy groups, and then anomaly detection. You have things like searching for transient. There are different types of transient. There are a lot of projects happening. So this gives you a bit of it. This is just purely text. There are many tools for doing machine learning. And number one of them, if you're talking about maybe basic machine learning, the most popular amongst them is Scikit-learn. And then on the other hand, in case of where you are looking for high computing infrastructure or hardware, you start talking about deep learning. And deep learning, you have things like TensorFlow, PyTorch, and there are also many other tools there. But today, TensorFlow and PyTorch seems to be ranking in the number one. So these things are there for you to consume. Now let's go into a basic example. Here is one example on Scikit-learn. What is Scikit-learn? Scikit-learn is a Python library for performing machine learning tasks. It is very vast. It has been in development for, I can't remember, for years, and it is ideal for doing a whole lot of the machine learning tasks that you want to do. And it is in Python. So remember, you have been learning Python already. And then at the same time, not just that it is in Python, it has tons of documentation. So if you look at this notebook, if you click the link here, let me see this link here. It takes you to the documentation here. So this Scikit-learn is a machine learning in Python. They have tons of examples. They have classification, regression, clustering, dimensionality reduction, model selection. So these are different sets of examples. Now, if you click this, you can begin to see types of models, linear models. You can see things like linear models, support vector machines. They have different types of it, classification, regression, and the rest of them. Let's look through that, but then that is not the focus of my class now. Now, when you have a data and you want to perform machine learning tasks, what do? You need to train. You need to train, and then you need to train, and then you need to also evaluate. So this is where machine learning comes in. How do you train a data set? How do you load a data set? Some of you already know how to load data sets. You know how to read a data. If you have a CSV data today, you know how to read it in NumPy, I believe. You know how to read with pandas. So that is a great start. And then what you need to also look at is what features are relevant for my machine learning task. And one thing about machine learning is that you don't just take a random data and then you start training. You need to first and foremost understand the data sets. the objective, the science of what you want to, because this is why the field is called data science. You need to have a background knowledge. Even if you don't have, you need to spend a little amount of time to go through articles, go through research papers, go through documentations to understand the kind of data, what the data is, what it can be used for, how was it collected. In that case, what scientific objectives, then you can begin to understand the kind of objectives you can achieve with the data. So here is just a demo showing you, a quick demo showing you how to get started with machine learning. So the first one gives you a text, and then the second one gives you how to get started. In this example, we are using a toy data set. Now, this toy data set typically just does one thing. Some of you have already played with it. I remember in previous lecture, the last time, you loaded things like iris data set. So you need to import data sets. You need to import, in this example, we're using two examples. We're using k-nearest neighbor. We're using support vector machine. Now, these are different types of machine learning algorithms. If you're hearing for the first time, please don't be scared. Don't be scared. You have different types of machine learning algorithms. Just like in every field, you have different types of theory, you have different types of laws. So you also have different types of classification or regression algorithms designed by different people. Okay, so don't be scared. Yeah, just like in the last lecture, in your time series analysis, you had the concept of things like Fourier transform, you understand, and things like Lumskargo periodogram. These are actually designed to help you achieve the same thing, but maybe they are also related, but maybe slightly different parameters. So don't be scared. All you need to do is to maybe just do a quick Google search. You'll be able to understand the concept and the differences in all of this. So in this example, we are trying out things like basic regression and classification. So what we've done here is load iris datasets. So the iris dataset is the dataset that you're familiar with. We load the iris dataset. We also load the handwritten dataset. Handwritten dataset. So here's an example of the digits dataset. This is actually an image data. This is more like this is more like it's an array, or more like a tensor-like array, because it's more like an array in an array. You understand? So you can see here it comprises 1,797 unique objects, and then 64. Each of them has 64 features. So now that's it. I think there's also an example. Yes, this is an example of showing you how that data that you're looking at, this is how it looks. So this is just a one-off example. Let me play around with this. I think this is supposed to be the last one. Let's see what this one looks like. So what shape are you seeing here? This looks like 0, right? This looks like 0. And then this looks like, sorry, I'm very pardon. This probably looks like maybe 5 or 7. I can't remember exactly. So this gives you an idea of handwritten images. So those numbers you're looking at up there is actually can be represented as an image. So don't be scared when you see them like this. This is just us looking at one of the arrays. This is all looking at the target. So you can see you can see, oh, this is beautiful. Now let's look at this. This is us reading the first item here. This is us reading the first item here, right? And let's also read the first label, true label. Oh, sorry. Yeah, so this is us reading the first label. You can see the first value is actually 0. And then when you run this, when you run this, let's run the first one. You're going to see 0. So all these values you're looking at here is actually, this is the true representation. So you're looking at the pixel values, and then at the same time, you're looking at the image shape here. Now, but this is not the major focus of this work. I just want to tell you that how those image data can also look like. Let's try and do a bit of the learning. Let's create an estimator. So like I said before, you have a data set. We have collected a toy data set and want to see what machine learning can actually do. We have imported the support vector machine module from Scikit-learn, and we have defined just two parameters, gamma and C. For more about this information, I think I also provided a link here. So this link here will take you to the full information about this very module, and then you can read more about it. And when you run this is you creating the estimator, because this we want to classify something here. We call this support vector classifier. After creating it, we fit the data. So this is just the first data, the first last row, and then this is just the last this is the data, and then this is the labels. So what we call features and the labels, or inputs and outputs. Maybe some people, depending on your background, inputs and outputs. So you do this, and then it learns from this, and then boom, you're good to go. What next? You use that model. So this will create this estimator. It will learn from the data. When you do fits, what you're saying is, please, I want you to look through these data and its properties and learn something from it. And then after that, you call it again to predict. And then now you're calling it to predict, and it's telling you that this is a 8 value, right? Now, I've shown you this earlier. Let's do this for iris datasets. The iris dataset is also one of the freely toy datasets available from Scikit-learn. It's not just in Scikit-learn. I think you can also fetch it from Pandas and many other framework out there. So it's more like some of the very good examples to get started with it. I think it has roughly 150 rows of data. So it contains the plant's length, width, petal, sepal length and width, and petal length and width. Some of you in agric science or biology might understand this way better than I do. So we have the targets here based on the classes. So I think the classes are usually say something. I can't figure that out here, but you can read more about it. And then what you do is this is also inspecting the data. When you inspect the data, we're looking at, okay, I see, we've already splitted this data, I think. This is us inspecting the data to look at the properties of the data. This is the shape. This is the label shape or the target shape. We've also looked at the features. Now it's important because, like I said, you need to also understand the features of the data set that you want to train. Sometimes you can also create your own features if you understand the domain very well. So you have the features and the target name. So here now it prints out the features name. So for each of those rows that you are seeing here, 1, 2, 3, 4, they do represent something: sepal length, sepal width, petal length, and petal width. And then the targets, these zeros and ones that you're looking at, is actually species, Setosa, versicolor, and virginica. You understand? So you can see how knowledge of the data can help you understand how to design your data. And then here we do the training. So we've already imported a module called train text split. So remember, sometimes you have your data. You can collect data over time, maybe 100 rows, maybe 2,000 rows, maybe 10,000, 100,000, 2 million, and you want to split it. So Scikit-learn also has a module for splitting data. So the train test split, what it does is that it takes the original data, the features and the labels, and then it splits it for you, such that you now have the one for training and the one for testing. Now, I want you to pay attention to this place very well that I've highlighted. This is how you define it. This is almost how you would do it in every field, whether it is science, whether it is astronomy, whether it is health sciences, whether it is aviation, whether it is engineering, whether it is business, finance. especially if you are doing classification or regression. So it does not change so long as you are using training, so long as you are using scikit-learn. This is basically how you're going to do it. And for some reasons, traits defining the variables this way have become a standard. So you don't need to reinvent the wheel, but you can still want to change it if you choose to. Then the test sizes, you say, okay, in part of the documentation there, I did mention that oftentimes if you want to split a data, you want to train, you can reserve maybe 80% of the data for training and 20% for evaluation, 70% of data for training and 30% for evaluation. The choice is yours. You can also do 50% training, 50% testing. These are just some of the things that you can do. So remember, this is a bit, you are experimenting. Okay, there's this one way of doing things. You need to also experiment. This is science that you're doing. So you can experiment over time and figure out what works, what gives you the best results. Then random state here is just one of those things that you do. In science, there's something we call reproducible science. So reproducible science is something that you do in the process of your experimentation, such that, or some of the guidelines that you follow, such that someone else can follow exactly what you have done and achieve the same result. Okay? One thing I need to understand about this computing systems is that even though they've been designed, the precision can change certain times, but because maybe, these things actually work as random, but at the same time, you need to also make sure that you're able to maintain the random states or keep the random states the same. So that is what this random state is doing here. So if I say 42 here, what it means is that if you follow my step in this notebook, we are going to achieve the same result, not close to, but exactly the same result. And it is important because these are some of the things that is questioned, maybe when we are doing science, like this work that you have done, either in the lab, this data that you've collected, does it follow a reproducible process such that if I follow the terms and conditions, that I'll be able to achieve the same result? So that is what it is doing there. So you can choose to change it to any value. 42 is just one of those common things that people have been using. So it's something that you can change. And then here, we have performed this train test split. And what we have seen here is that we have splitted the data. And then here, we are looking at the properties of this data now. If this data was originally 150, as you can see here, now we have splitted it, and then you now have 120 rows for training, 30 rows for testing. They still keep their feature properties, but they now have all of these things. Now, why are you doing this? Remember, after training, you need to predict. Now, predict is taking the one that you have classified, that the model did not learn from. You want to see if they can actually predict it, because it did not see the data, but you want to see that from the other data it has learned from, can it predict this data? That is what tells you whether your model is learning or not. It's just like you, after going through your classes and then to tell you, hey, come, we have quiz tomorrow, or we have a test, we have an exam. That is you being tested to learn, to see if you have learned what have been taught to you. So it's just the same process, follows the same process. Then we have another example here where we try to do things like using a different, remember in the first one, we use support vector machine. Like I said, we have multiple models, multiple algorithms in machine learning. And then this one is a case of nearest neighbor. So just like the name suggests, nearest neighbor is, it looks at this data set and look at the features and begin to say, okay, let's actually see how they all relate to each other. So here you have a case of n neighbors. We have 3 classes. So we say n neighbors of 3. These other ones like weight, distances, they have Minkowski. So you can read more about it here. And then we have different types of algorithm. This is more like the processing speed and the rest of them. So if you do this, you can see it follows the same step. You initialize the estimator, or initialize the model that you want to use. You pass in your trained data, the features and the labels. And when it is done, you predict with the what? With the test data. Now, when you predict with the test data, you get your predictions, and then you now do what we call evaluation. Evaluation is where you want to check the performance. Remember when you splitted this data, you had the labels for testing. So you now compare the predictions from the X test and the true values. And then when you do so, you should have values ranging from 0 to 1, where 1 is very efficient, 0 close to 1, close to 0, more like it's not learning anything. Even 0.5 is not really learning anything, it's just where it is. It's not able to disentangle, it's not able to find pattern in the data, because what you are doing is pattern finding. You want to see how these things are related. So it's more like a graph. So you're trying to like look through and see how these things are related and able to like partition them separately. So if it's not able to do so, then you know it's not learning. In this case, this is 100%. But like I said, this is a toy data set. Okay? If you, in real world, if you have a data set and your model is 100%, sometimes you need to also pay attention. You need to go back and figure out what is going wrong, because sometimes it might also be that you are overfitting. We have other terms in machine learning called overfitting, where your model, maybe there's a lot of parameters, so it learns the whole data fully, but is not able to generalize in other data sets. It hasn't seen. So it might say, oh, in this 100%, but in the future or later on is not able to perform poorly. Okay. So so this is just some of the examples. We have different examples of evaluating this model. We check things like precision score and the confusion matrix. So these things have been described in the third notebook, 03. So you have this, and then you want to save this model. How do you save the model? To save the model, if you feel like, oh, this model you have trained is so beautiful, you can save it by either calling job-lib, which we've imported from the beginning of this notebook, or Pico. So you import it, you just say dump, define a name for it, and pass in the model name. You see, we'll call this model KNN here. So we have trained it, and then we want to save it, we'll just save it as KNN, pass it the model name, and it is saved. Boom, it is saved. Now they can come here and see that the model is saved here. We'll call it KNN iris model.joblib. Very small model, 11.1 kilobytes. But like I said, this is a very simplistic case. Let's quickly look at one other example before I leave the space for Priya to come in and take you on a bit more background on the astronomy and the rest of them. I just we made this is an example because we used toy data set, right? Now this is an example of another example where we're trying to do regression. And here we choose to use a Redshift data set. This data set have been collected with, I think this was collected with SDSS. So you're looking at the colors of galaxies and trying to see if we can use it to predict the redshift of the object, the extragalactic object. So reading through, I try to give basic explanation. So this was called from somewhere. Actually, I need to also add it here in the latest version of this notebook later today. This is just a description of what the scientific concept of what redshift is. Some of you in astrophysics do understand this. When you're talking about distant objects, extragalactic objects like quasars, AGNs, and the rest of them, galaxies. So here is just showing you the filter, the filter information from SLAN. And then you see the different kinds of filter, U, G, R, I, Z, color mag. These are just magnitudes. So different magnitudes. And then here we import this data. So if you are running this notebook on Google Colab, please, you need to run this. You need to run this cell. But if you are running it on your PC, the data has been provisioned already, so you don't have to run this cell. So I'm running this on my PC, so I do not have to run this cell. So we have this photometric redshift, SDS photometric redshift data set, and then we try to clean the data set. because there were a lot of gibberish in the data. You can see it's going to give you some warning. Do not be scared. It's because this data was prepared over 10 years ago. So a little bit of the things in the algorithm itself has changed. And then here we define a color. So most times in astronomy, we have what we call color. You have encountered it, I think, in the week 2 and week 3 of this program, where you plotted the color magnitude diagram. So color is the difference between two magnitudes. It tells you how effective. Most times it's ideal when you say blue and red color, or the normal color you have in the red, green, blue. So it tells you how there are changes in this magnitude. So oftentimes, depending on the configuration, we can say whether an object is red or blue for stars. So red means it is less hot or not that luminous, or faint, and then blue means that it is very, very hot, super, super hot for like very massive stars, or things like gamma ray systems or Fryette stars. So we have, looking at these colors, we've defined them. So we've loaded this data also in pandas. Now you can see how it looks in pandas. The original data was in a NumPy array format. Now we've loaded it in pandas. We've also created, this is the original data. From here to here is the original data. Now we have created our own features. Remember I told you, whenever you're doing machine learning, you need to also understand the domain, the area of the data, so that you can, the science behind the data, so that it will help you know how to create even new features. Because the better the features, the better your features, the easier your machine learning task will be, because it will be easy to learn quite well compared to when you've not been able to do a bit of data transformation. Yeah. So, or feature engineering. These are more complex terms: feature engineering, feature scaling, and the rest of them. But it's not part of this course. But I also provided a link where you can also learn about these things in the notebook. Now, what we're trying to do here is that we were trying to do a bit of data visualization. It's also important, when you have your data, do your exploratory data analysis. It is beautiful. Why are you doing it? You need to remember, when you visualize things, when you study the data, you can be able to understand relationships. Learn as humans first. It's important before you delve into or jump into doing the machine learning thing. Learn as humans first. Now we are looking at the original features or magnitudes of this data set. You can see the distribution. You can see you have a case where you have some dominant ones. You can see the weight of the distribution as well. This is a case of the color index that we have created. It's a bit not super extended. It's a bit closer to each other than the other one. Then this is the redshift information. You can see that the majority of the objects are within 0.25 redshift. This data has been cleaned up. So these are just basic visualization. Because why you do this is that sometimes when you see something that is odd, and you think it's going to cause problems for you, you can also drop them. If you spend your time here, you see I did a lot of cleanup in this data. I removed a number of things that could cause problem, or not even allow the machine learning task to even work. This was originally, I think, close to 400,000 or so rows, but at the end of the day, we only had, I think, roughly 13,000 rows. So that tells you that the majority of the data were dropped. Why? Because I noticed some weird features, like where a magnitude is minus something, or where a magnitude is 0.00 something. No. You can't get such magnitude for a galaxy. You understand? And it doesn't even meet SDSS filters. I'm not sure exactly the limits it can go, but I'm not sure you can go for things around less than 5 or 7. So you need to understand this domain knowledge because it helps you. So we now, after doing this, remember, we imported the train text plate, defined our features, defined our targets. So remember when I said X, Y. So now this is going to be our X, and this is going to be our Y. This same data that we have seen here, right? We have selected the feature that we want. We don't want to take all of this data and train it, because it probably will not learn. This will not help us. this error was not going to help us. So this is the one we're interested in. So it has been defined here as features. And then this is targets. And then we remember the train test plates, the same method. You see, it didn't change. Passing the features, X, Y, and then we split. So when you split, you now have a training set of 10,624 and a test set of more than 2,500. Now, the next thing we do is to perform train the model actually, but we had to look at the evaluation because it's important, because I didn't just want to jump into training. We have done that before in the previous notebook. So we had to look at, for regression, how do you evaluate the regression problems? There are a few common ways to evaluate and see whether your model is learning very well or not. Evaluation is very, very important in your machine learning task. So we have a couple of ones. They are mentioned here. We have the mean absolute error. We have the mean squared error. We have the root mean squared error. We have the R squared error. Now, our coefficient of determination. For some of you who have done statistics, I'm very sure you may have encountered this. Even basic statistics will tell you a number of times what these things are. They've been defined here actually, but over time, I don't even have time anymore. I think I've used up my time. Sorry, Priya. Let me just round up. So the R square is the most important one. It more like gives you a sense of the direction of your model, more like the accuracy. These other ones are also important. The R root mean square error, it should be, if your model is learning very well over time, it should be dropping. Your R square is also expected to increase. It should go from 0 to 1. The closer it is to 1, the better your model is, and especially for regression models. But if it's somewhere around 0, it's just all of those things, then you're not doing quite well. You have not created or prepared your data in such a way that it can learn from it. Again, it is not every task that machine learning works on. So we need to also have that. You need to think about problems that machine learning can solve. So here we go through training the model. And after training the model, here is just defining the function. It runs through and trains this model. For each of the machine learning methods that we regression, we use linear regression, ridge regression, lasso regression, random forest, k-nearest neighbor, decision tree, and support vector regression. All of these were applied here. And for each of these, we have different mean absolute error, root mean square error, and the R square error. Now, if you pay attention to this is for linear regression. This is 0.45. Poorly performed. You can see how you can see the true redshift. You can see the predicted redshift. You can see there is no relationship at all. It is flat. It is flat. So it's no relationship. Very poor. This is the residual. Very wide. That also tells you that this is not doing quite well. And then this is the lasso regression. All the linear regression methods were poor because of time. So let me rush. And then we have all of this. So you have the k-nearest neighbor, which did show quite improvement. Now, this actually shows you that there's a great improvement here. The true redshift and the predicted redshift did perform very well. How do you know? You can notice that the root mean square error dropped significantly. You can see here it was 0.35. Here it's now 0.17. And you see that the R square score is high, 85%. And if you plot compare the two models, you can see it did predict to a great extent, but it did not really. There were also outliers here. It performed poorly for a number of them. You can see, but it did quite well. To an extent, what it means is that if you give it this data, 85% of the time, it is going to at least generate good predictions for you. You can see the residual here, quite small and well centered. So this is for decision tree. We also have for random forest, and this is for random forest, and then we also have for support vector regressor, which also did quite well, but not as good as k-nearest neighbor, decision tree, and random forest. Now, this is just a basic example. Here is also an example that shows you feature scaling. Like, I want to scale this data. These are just for academic purposes, also well explained. And an example was also shown here. This is you scaling the data and seeing if it's going to lead to an improvement in your data. In that example, we didn't see we didn't see a lot of improvements except for support vector regressor, where it improved from, I think, from 71% to 82%. So it all depends on the algorithm that you want to use. So a lot of example resources have been shared here. Please go through them. Kaggle has an introduction to machine learning course where some of these things have been described. And a number of the materials used in preparing this notebook were also borrowed from there. We have the Google Machine Learning Crash Course. We also have this example notebook on in Kaggle that was developed by somebody as a contribution that describes a bit of the evaluation methods. And then here is also a discussion on tuning your model. But because of time, I will not be talking about it. We did a couple of examples. It's just the same data set, but we did what we call hyperparameter tuning. If there are functions to call to do your hyperparameter tuning and the rest of them. So please, I'm going to stop here. Please put your question in Slack and put your question here in the chat. I'll try as much as possible to respond to them. So let me hand over to Priya. And let me also note that these things, what happened in this notebook is not different from what was shown in the previous one. The only thing that happened there is that we try to be a bit technical in terms of trying out different parameters for training this model to see if we can gain any improvement. Sometimes these are some of the exercises that you need to do. It is not compulsory, but if you think your model is poorly learning, then you need to do some of these things. Thank you very much for listening to me and make this presentation. So Priya, I'm going to stop now and then you can take over. Hi, Priya.
Thank you. Yeah, Daniel, thank you for a very comprehensive, detailed talk. We'll start now, Priya and me.
There's a question.
So, yeah, are there any questions for Daniel?
I think they can leave the questions in the chat. I will respond to them, and so that because we are racing with time. Yeah. So Najam, you can proceed.
Okay. Yeah. Okay. Just a minute. Where is? Okay. So we have heard pretty much detailed talk on machine learning and various tests, which Daniel spoke about. And in this presentation, let's see a few slides, which may be a repetition to stress a few points. But essentially, we'll be focusing more on machine learning in astronomy. So we'll discuss some specific cases where all the techniques which have been discussed by Daniel can be applied to. So before we go to the next slide, have a look at the graph on this. And what you see on this graph are histogram of publications. So in gray, it gives you the publications of all articles, and the blue part of it, which is marked, shows how machine learning is being used in astronomy research. So you can see that from 2000, where machine learning, the number of publications them were very less, to somewhere around 2024, 25, number of publications have gone pretty high. The article count has gone very high, and you can even see the blue bars rising very steeply, an exponential rise. Yeah, so this indicates how the number of publications or the kind of research which is happening in astronomy and the importance of machine learning in that. The reason for this is, like Daniel said, the amount of astronomy data has been increasing. In 1980s, we got it in megabytes. There was CCDs which were collecting data. In 1990s, it went into gigabyte. 2000 and went to terabytes. 2010 went to petabytes, and now in 2020s, we are going to exabytes. So there's a tsunami of astronomical data which is flowing in, and astronomy over the years has changed from data poor to data rich science. And uh, since there is tremendous amount of data, it has become essential for us to use these big data sets and to interpret the complex astrophysical problems by using sophisticated statistical techniques and technology, right? So programming has become very essential. And in the present age, uh, Python is getting very popular in astronomy circles, and that's why we are stressing a lot on using, doing machine learning or doing statistics or whatever we have been discussing in all the other topics is with Python. So, as we collect huge amounts of astronomical data, it has gone beyond human capacity to analyze without help of machines, and it has become essential to teach or train computers to sift through the data, identify important patterns, and find connections that might be otherwise missed out by human mind. And this process is called machine learning, and it is an essential aspect of artificial from 19 artificial intelligence is not new. People have been talking about artificial intelligence since 1950s onwards, and so a period from 1950s to 1980s is, I would say, the era of early artificial intelligence, which stirred excitement. In 1980s to 2010, machine learning begins to flourish. And 2010 onwards into present, we have this deep learning. Yeah, it has become this is driving the artificial intelligence boom. And as you see on the graph on top, machine learning has applications in almost everything: automated data translations, medical diagnostics, and email spam and malware filtering, and so on and so forth, traffic predictions, and so on. But what we are interested is astronomy, right? So machine language, as Daniel has mentioned, we can break it up into supervised, unsupervised, and reinforcement. So supervised machine learning is it's basically task driven. You have data. We'll look into some examples how it gets applied in astronomy, where you train machines to see patterns, and then you using these training sets, the machines try to identify from a larger sample of sets and see, and we will see that there's a tremendous improvement in predictions. And you have unsupervised when you don't have training sets, and we have reinforcement which learns from mistakes. It's a mixture of two. In the supervised learning, we can have problems of classification or of regression, right? For example, if we have data, we have supernovae, type 1, type 2, type 3 supernovae, or type 1a, type 1b, and so on, and we want to classify them. Or suppose we are looking at a set of galaxies and we want to see the different galaxy types. We have to classify into spirals, lenticulars, ellipticals, and so on. So we use machines to see the patterns. We train them first, and then the machine identifies these objects, right? So we'll see some examples as we proceed of classification. Other one is regression, where you have you may have a dependent variable, and you may have one or many independent variables, and you try to find a relation between them, right? So usually regression is used In fact, it is used, not usually, but it is used continuous values, ages of or redshift values, where you have a continuous range of values, and you are trying to fit if you have regression, linear regression, or different types of regressions. The most simplest one is where you try to find a linear relationship between an independent variable and a dependent variable. Try to fit a line which gives the least fit from of observed from this line is minimum. While this classification goes when the data is discrete, where you can break them into different categories and so on, right? So for example, there is this Galaxy Zoo project, which any one of you can participate in that. And basically what it does is there's tremendous amount of information about galaxies. As we see here, galaxies come in a variety of shapes. There are spiral galaxies. There are you can see a filament like galaxies. There are circular galaxies. There are elliptical galaxies, and so on. So this essentially it sometimes these Galaxy Zoo projects even uses human beings to classify them. It initially trains them and shows them how a certain galaxies can be seen as a barred spiral or a normal spiral or SA, SB or ST galaxy or elliptical one, and then the humans sift through this data and put them in bins. The other way of doing it is through machines. The machines are taught to see the structure of a galaxy, and they match the pattern, go through this immense amount of data which is available. There are trillions of galaxies which have been observed, and it's not humanly possible for people to sit and classify them. So the machines are being trained to sift through this data and put them in different bins depending on their morphology. Another place where it is being used uh, is, say, classification of variable stars. So the stars, variable stars can be broken up into intrinsic variables or extrinsic variables. The intrinsic variables, they are further, yeah, these are the two major groups. Then you have classes of pulsating stars or eruptive catalytic stars, which are the intrinsic. Intrinsic variables are eclipsing binaries or rotating variables, right? And further, the pulsating stars are Cepheids, RR Lyrae, RV Tauri stars, long period variables, and so on. And then long period variables again break up into Mira types, semi-regulars, and Cepheids are type 1 classicals and type 2 uh, Virginis, and so on. So, looking at the light curve, which is shown on the left side, you can each binary has a signature, a typical kind of a light curve. So what we are seeing here is the variation of light. These are, as the term suggests, the stars show variability. They become bright and then they lose their brightness, they become faint, and then they rise up again, and so on. And looking at the profile of the light curve, you can say whether it's an RRC Lyrae or RRAB Lyrae, or whether they are C feeds or Mira types, and so on. And machines are being very successfully being used to classify them, right? So, an advantage of using machines is it can go through repeatedly. It can, once you have the code given, it can pick up the light curves, draw them, match the patterns, and predict which kind of a objective it is, uh, very fast. So you can classify many of them in a short time, right? So looking at these light curves, you can see Kepler 4b, which is one of the objects. The light curve, it's a very flat kind of a one, while Kepler 5b shows a bigger dip. There's a bigger drop in the intensity, and so on. So by looking at this, how shallow the curve, the dip is, or how deep it is, it gives you parameters of the star and the eclipsing object, right? The size of the eclipsing object, the size of the star, and so on. And the orbital period and all the orbital elements can be got by looking at the light curve. So this is tremendous amount of information which comes in, and this is where machine learning is very effectively being used. Coming to examples for regression, we have uh, supernovae, and we are looking at their recession velocities, and we have these data points, and we try to fit a line of best fit where the deviations from the squares of the deviations are minimized, and right, so basically the line of best fit. So uh, this gives us, this is how Hubble, when Hubble and Emerson had predicted the expansion of universe, the sample was very few, and they were very brave enough to fit a straight line to show how the data that it's showing a linear fit, right? But today we have many more objects, and it becomes essential to use some kind of algorithms, computational techniques to fit the line of best fit, right? So another very interesting problem is the three-body problem from celestial mechanics. This refers to three masses. Suppose we have three masses. For example, you have Sun, Earth, and our Moon, right? Or we have M1, M2, and M3. And if you know their positions and velocity at a given time, the question is, can we predict the motion of this three-body problem, right? And it has been shown that when you have two bodies, suppose you take just Sun and one planet, or M1 and M2, just two objects, then you can write the equations of motion and solve them. But the moment you have three bodies, you cannot find a closed form uh, solution. You can't find a general closed form solution. So this problem has been an open problem for the last 400 years and has played a very central stage in celestial mechanics and development of a lot of mathematics. What was realized is, though you can find particular solutions for a three-body problem, but you cannot find a general closed form solutions. And interestingly, machine learning is being used to solve this problem. So there are some analytical methods of doing it, but it goes into a lot of computation. But machine learning has been able to give exceptionally good results to these solutions. So basically, you train machines with different masses, with different initial velocities and different positions, and show what the outcome is. And this is trained for many such things. And then using that, it can predict the motion of this three-body system uh, uh, for a new set of initial conditions, right? So uh, this has been a revolution, and the solutions of the three-body problem through machine learning are being taken very seriously, and they play an important role when you study star clusters and dynamics of star clusters. Another interesting example is this convolution neural networks are being used. They have been used to construct the image of the black hole, the first black hole images, which you remember we saw, which had captured the imagination of everyone around. They use these convolution neural networks. They are a class of deep learning algorithms which are quite efficient in recognizing real world objects. And CNN are the best neural nets for interpreting and understanding images. And the image which was constructed was used by the Event Horizon telescope team. They developed these images computationally using these CNNs, right? So this is yet another place where it comes. But there are various issues in machine learning, and one has to use machine learning in a very discreet and in a careful way, because you can't use it as a black box. So when you are using machines to classify stellar spectra or binary eclipsing or variable star uh, curves or classifying galaxies and so on, it's very essential that we do it carefully, because it can lead to tremendously wrong results if we are not careful, right? So, what are the issues? Some of them are listed here. So, it's important to know what algorithm can approximate functions well and when. This is very essential to know. How does the number of members in a training set influence the accuracy, right? Then the problem of representation or the problems of feature extractions have to be taken care of. And intentions and independent learning issues have to be considered. Integrating learning with systems, and what are the theoretical limits of learnability we have to keep in mind. And how do you transfer this learning? And this method of continuous learning, right? Human beings have a method which we have, there's a continuous way of understanding, evolving, and categorizing things. And in the same way, machines also have to be constantly trained and retrained, and this reinforcement method is used to get best and better results. There are various special cases which we should be looking at. Priya, you will handle the star clusters?
Yeah.
Yeah. Okay, now I'll give it to Priya. So she'll talk to you about some of the other cases, and then we'll go to the Python, the Jupyter notebooks. Okay, thank you.
Yeah. So thank you, Najam. And now what I'm going to be doing today is I'm going to take up a special case of
Unmute.
where
You are mute. Unmuted.
I'm unmuted. So I'm going to take a special case in which we actually used machine learning. This was for the thesis of one of my students who defended last year. And this is basically a kind of a guideline to students about the Capstone project, which I know all of you are thinking about. And so I tried to describe this work because, you could actually, there are 4 papers in which this work has been published, and you can actually look in those papers, and I'll try to explain to you what did we do in this work. Okay. So, this work was basically based on what are called star clusters. Okay. And star clusters are interesting objects because they are the basic building blocks of galaxies. And if you want to understand the formation and evolution of galaxies, it's good to understand what is the deal about these star clusters. So what are the types of clusters? They are typically open clusters. This is an open cluster. Many of you all may have seen Pleiades. Pleiades is the one open cluster that can be seen with naked eye. This is in the constellation Taurus, and it's visible at this time of the year. If you look up, you may see it. And it's a very beautiful cluster. So open clusters are nice objects like that. Globular clusters are much more denser. You could also have what are called associations. Now, to study these objects, there's a very important project which is on, which is the Gaia satellite, which is being used. And the Gaia satellite is a satellite by European Space Agency. It's been out for almost 10 years now already. And you basically have two identical 3 millisticks. Now, what it basically does is it gives you very accurate positions of stars. And because it very accurately measures the positions of stars, it also measures their velocities in the plane of sky. So in the plane of sky, it can tell you what is called the proper motion in RA and what is the proper motion in DEC. The telescope, which is on the satellite, also has a spectrometer with which it can measure radial velocities. But the problem is, like, the photometry is available for stars to about 21st magnitude, but the spectroscopy is only for up to 14th magnitude, right? So we don't have spectroscopy for all the stars. But the accuracy of this telescope is so great that you actually get what are called micro arc second accuracies, okay, which is 10 power minus 6 of an arc second, okay? And therefore in distances, it gives you a very good accuracy because distance is approximately 1 upon the parsec, right? So that means if you're getting, if the order of 10 power minus 6, your distances are 1 upon that, that is about 10 power 6 parsecs. And so you could, like, you're actually covering the whole size of the galaxy, right? So this gives you an ideal sample of studying about 1 billion stars of the galaxies, for which it can give you accurate measurements of the distances of stars and their velocities, okay? Now, why is this important? For these very star clusters we were talking about, like if you look at this image, you can see a whole bunch of stars in this. The question is, which of these stars actually belong to the cluster? How can you find out that? And that's what we call the membership problem. Now, the membership problem, there are different ways of actually studying the membership problem. The safest one is that if all these stars were born together from the same molecular cloud, they should be obviously at the same distance and they should be moving around with the same velocities, right? So Gaia actually gives an answer to this question of membership, because if stars belong to the same cluster, they are from the same molecular cloud, they should be at the same distance and have the same velocities. Now, Daniel already spoke about it, even Najam spoke a little about it. How do we basically find out members, right? So it was already mentioned to you, supervised learning. What is supervised learning? Is that, for example, if you have images of 100 dogs, right? I identify, say, these 100 images and tell you which are the images of dogs and which are the images not of dogs, right? So that means I already have labeled data for which I know what is what, right? And then what happens is, because I already have these 100 images of dogs where I identified dogs, if you then give me images of 1,000 animals, I can identify which of them are used, which of them are dogs, right? So what you have is the set of 100 is like what we call a training data set with which you can train you. And then based on that training data, you can actually identify the objects in the other set, in a larger set. Okay. Now, this is a very effective way of actually categorizing data, for the simple reason is that because we have labeled data, like we did in the previous case, I think it was mentioned to you, where what you do is you actually do what is called a training set, and the training set is not all the data. Okay, so for example, if I have 100 images, I only use 70 images for the training data. Okay, and then the remaining 30 images, I actually use it for validation of the data. That means if I've identified in my 70 images, I've identified which were the dog or not dog images, right? Then for the remaining 30, for which I know the answer in advance, right, as to which are the dogs, which are the not dogs, I can check how well has my machine, when I supplied it my 1,000 plus 30, I can check for the 30 ones which I knew, how many of them have been correctly identified, right? And so therefore what happens is this gives us a very good handle on the data in the sense of validation. That means I can validate my data, check which of the data is, how well does it do it? So for example, for my 30 images, right? If I know that 28 of them are correctly identified, so I know only 2 went wrong, right? So I know that out of 28 out of 30 are being done correctly. So this is a very effective thing because number one, you can train your data, and number two, you can validate your data. You can estimate the accuracy of the data, right? The only problem with supervised method is that your training data needs to be good. Now, Najam mentioned to you another example of supervised learning, which is, for example, the Galaxy Zoo project. In the Galaxy Zoo project, we have a training data set, which is done by humans who identify which are the spiral, which are the elliptical, which are the barred galaxies, etc., right? And they are used as a training set. So then if you have 1 trillion galaxies, you use your training data set to actually identify those types. And accordingly, you can validate it and check. Okay, so the only problem, like we said in this, is the problem about how good is your training set. Because if your training set has errors in it, then you will obviously get bad results. So based on that, you can actually see how good is supervised learning. So what we actually did in the first paper, which is shown over here, membership of open clusters in random forest, you can Google and you can directly get the papers. They are all available on the net. So what we basically did is we took 9 open clusters, which are listed over here. They had a big range of ages as well as galactocentric distances as well as galactic latitudes and longitudes, because we wanted to see how well does it do it for different locations and different positions. Now, there was an earlier paper by these authors, Cantat Gordon, 2018 paper, which actually used Gaia DR2 to identify members in these clusters. So these were the ones we used as our training set, okay? And then we used Gaia DR3, that's a newer data set, to actually run a supervised classification method, which is called random forest, okay? I won't go into details of random forest, but you can read about it on the net. And on that, we got these very good results. You can see these orange stars are the stars which were found by by the training data set. What we did is we looked for a larger radius in the same area of the cluster, because often in the outskirts also you do have a lot of members. And the training set was only up to 18th magnitude, but we stretched it because now we were using DR3. We took it almost to 20 or 21st magnitudes. So we actually used that. So we got deeper and we got larger in size. And you can see the difference in plots. The orange stars are from the training set, and the blue stars are the new things which we discovered using our using our analysis. You can see how, for example, over here you have the orange stars are the ones that were found for the training set. The blue ones were the extra ones which we found out using our method, and the green is the combined. So you can see that the peak that we are getting is approximately very similar to what was there for the training set. It has the same kind of behavior. We use this to do color magnitude diagrams as well as looking for structure within these clusters, okay? So when we plotted in proper motions, etc., we actually looked for whether, like for example, here I have 2 clumps. That means there are 2 kinds of motions happening over here, right? So we try to look for spatial structure as well as kinematic structure in these galaxies. So in these clusters, sorry. So orange was the training set, blue was the additional stars, and green is the combined one of the training set as well as that. So you can see that you have this other structure. The CMDs were also very, very useful because, for example, in this cluster, you can see the original CMD only had these stars, but once we added our additional stars, we see very much these additional new stars, which are the ones. Some of them are pre-main sequence stars, and they're different kind of, you see these other variable stars, which you can see over here, which were not identified by the earlier things. There are what are called blue stragglers also, which lie above, they are brighter than the topmost main sequence stars. So we can find blue stragglers, you can find pre-main sequence stars, you can find various variable stars, which are members of these things. So validation also, we found out different methods. That means for the clusters, we found out their radius, the members before filters. We applied some quality filters, which are described in the paper. Members after the filter, what was the ratio of the new members to old members, which is listed over here. And then you can see the precision. The precision is, remember what I told you, that when we divide the data into 70-30, we check of the 30, which is 30% of the data, how many of them are correctly identified as members. So we use that to get the ratio of the precision, and you can see the precision over here. So it's like only these two clusters for which it's like in 80s, but otherwise you can see it's plus 90%. Yeah, but this gives you a good idea that in reality, this is what you actually achieve. You do not, there's a limit to how well can you get the validation. So what we did is we increased the number of members 2 to 3 times, improve accuracy, etc. So one typical Capstone project one can do is you can have a look at this paper and you can run it for some other clusters, right? And see what are the kind of values you get for your thing, and see what are the ways in which you think you can improvise on the work done in this paper, right? What are the things which you think can be improved in them? What can give you better results? And in what way can you enhance it, right? We continued this work with this thing that it's to assume, like I told you, the problem with supervised learning is that if your training data set is bad, you may have a problem. And therefore, why not try unsupervised methods? That means don't assume anything to be a member, just start with the data as it is. So we used unsupervised methods, and we basically use what are called clustering methods, okay? The clustering methods basically based on this thing that in that parameter space, that means RA, DEC, proper motion RA, proper motion DEC, and radial velocity as well as parallax, members of a cluster will lie close to each other in that n-dimensional space. So we basically look for clustering or grouping. So one of the methods, and you basically want to see how does it work for all clusters, the question is, what is the field to cluster ratio, right? Because stars in that region, some are field stars, some may be background, some may be foreground, and which ones are the members. So one of the methods used is what is called the Gaussian mixture modeling. That, for example, if I have two mixtures, I have a cluster 1 and a cluster 2, then if they are both added on, I have this green thing. Red and blue are the individual ones, but green is the combined effect, which I can see. But if I say that there are two Gaussians sitting over here, I can fit them to fit the green curve. So what happens is, what I'm observing is green, but I break this into two things, which is the red and the blue. Okay, these are called Gaussian mixture modeling. So typically you can see this is a very good example. This is a cluster called M67, and you can see that the red stars are, when you look for clustering in this thing, we actually find two Gaussians. One is this Gaussian, the red stars, and one is the blue stars, which are the field stars, which are not members. And you can see how beautifully in this plot, you can see that the cluster members, they peak at this certain, it's a very thin peak which you're getting, which is for cluster members. But the field stars are distributed more randomly, and hence you have this is the distribution in parallax. So therefore the cluster stars are peaked like this, while the field stars are a much more flatter distribution like this. So this is the distribution in parallax. These are the color magnitude diagrams. You can see you have a very neat, nice color magnitude diagram for the members. These are the stars which I mentioned earlier, which are called blue stragglers. These are kind of brighter than these ones, but you can see the cluster already has a turn-off over here. So these guys are, but these variables are very easy to catch using Gaia data. And these are the field stars. So this was a paper with one of students. Almost them are with students. You can find this one also on the net, and you can see all the ratios of the validity, etc. So how well was it done, etc. We also defined something called a modified series. I won't go to those details, but there are various more details in the papers, and you can have a look at that. We also used another clustering technique called DB-scan. In DB-scan, what happens if I have a group of stars over here? For a certain star, I define an epsilon radius, and I define minimum number of members. If I have minimum number of members in the epsilon radius of a star, I call that a core point. But if, for example, this star, I'm drawing an epsilon radius for it, I do not have the minimum number of stars, like I have 4 over here, then this is called a border point. This guy over here, it doesn't sit into the epsilon radius of any star, right? Neither does it have number of stars within its thing. So this is what is called a noise point. So this is a noise point, this is a border point, these are core points. So for this group of stars, you can find the noise points and the core points and the border points. And based on that, you can identify clusters. So this was a paper which was published, and you can actually go through it and actually find these things where you can see that we have these three colors for the ones which we had with the DB scan, and the red stars are the ones which were there from the training set, just to compare to see how did we get it. So this is the one for M67. You can see we are going deeper, therefore you have extra stars over here, and you can see how well the Kull magnitude diagram gets enriched. On the same thing, so there's the good estimation made of how we get the parameters. There's also another interesting kind of job one can do, is that not just star clusters, but for example, you can look for star forming regions. Okay, so this is a star forming region called Serpens. Serpens has many young stellar objects. So what we did is we actually used the young stellar objects catalogs, cross-matched it with Gaia data, right? Found the parameters for those stars, used that as a controlled sample. This was done with early data release 3 of Gaia. And then we used ML techniques like DB scan. There are some other techniques also called optics and HDB scan. In a minute, I'll explain to you the difference between them. And we got the YSOs using this method. So like I said, we queried a 2-mass radius. We took these parameters. These are just for your reference. And we get the compiled list. So based on this, we actually cross-match this with data from 2-mass and WISE to classify these young stellar objects and see where are they this thing and how are they moving. So this is just an example of the various capstone projects that you can be doing using these things. Obviously, there's no deal that you need to necessarily do this, but the idea basically being that these are just examples of things you can do. Right? You can also do things like what you were shown was, if you're working with Kepler data, etc., you could have used templates of color light curves and use there to actually, look for examples of different variable stars, because all of them will have some kind of signature, these things. Okay. Now I just want to load this one. Okay, so if you see on this on the GitHub page, right? I think this file has been slightly renamed. I think it's called ML in Astro or something like that. Okay, it's been slightly renamed, but you can actually see it. This is basically an example of using Scikit-learn, okay, to do ML. Okay, what we are going to do next week when we again have another class with you on machine learning, there is a Python package which is called Astro-ML. Okay, Astro-ML, right? Okay, no, I want to do this 1 minute. Let me just show you Astro-ML. I don't want to. We'll actually be going through the GitHub page. I'll show that to you also later on. But basically, this is a machine learning. Scikit-learn can be used for anything, but Astro-ML. Oh God, let me just see. Astro-ML. Python. Okay, so if you can see over here, this is basically a package which is meant for machine learning, and this thing specifically for astronomy, right? So you can see it's a Python module for this. It sits over SciPy, okay? And Scikit-learn, it is above that. So first of all, you need to understand what is there in Scikit-learn, and then you'd understand what's there in this. And there's a textbook also which is associated to that. We'll do a little bit of this theory from that next week. And you can actually see there are various tutorials. We will run you through some of the tutorials. For example, there are some examples over here, dataset examples, etc. And basically in which you will actually see some of the things, right? But today we are continuing with Scikit-learn. Tomorrow, next time we'll do ml. So here you can see in this thing, there's a little bit we are going to show you on what is there in Scikit-learn. So I'll just pip install this. You need to pip install it. You need pandas and some of the data sets. So the first technique which I'm actually going to show you is a clustering technique in astronomy, right? And this is called k-means clustering. I did explain that to you earlier, but now I'm just showing it to you. What does k-means clustering do is, for example, if I have a star over here, right? I want to see whether there's a cluster, right? So what do? Is I look, for example, what is the distance to the first closest object, right? Then I look to the second closest object, the third closest object, the fourth closest object. Now, for example, if I had, I've actually generated this data using a thing called make blobs, okay? So you can see my XY is generated using make blobs. I'm making 300 stars with 3 centers and this random state 42. Some of our astronomers, if you'll see in most astronomy things, you will always have the random state to be 42. There's a reason why astronomers like 42, but I won't tell you about that today. So in short, here you have 3 blobs, right? So what happens is, if I look for this star, for example, this one is on the outskirts, but if I take one over here, I look for the first, say, 6, 7 nearest stars. I can actually find all these guys have, the number of stars in this vicinity, right? So what happens is I can fit it and actually use it to find clusters. So when I'm running my k-means, you can see I get a cluster of 3. The question is, how correctly do you do it? Supposing if I ran this for 4, right? Then you will see that this thing artificially breaks this cluster into 2 groups, right? Maybe these 2 groups mean something, maybe they don't. That is up to the user to identify. So machine learning is a very, it's a dangerous toy to play with if you do not know what does it do. For example, if I break this into 2 clusters, the data is sitting in 3, but if you see, then it forcibly makes these to be part of a cluster, which is definitely not the case, right? So it's always very important that when you run it, you should visually inspect it to see what it looks like. You can clearly see that these are 3 groups, and hence you put them as 3 groups. But in reality, what happens is you will also have points over here, and it becomes more difficult to verify whether this is, what is the k value that is the ideal value. So this is a nice data set. You have a clear 3, but in reality, you may have more. dbScan, I'm showing you the code for dbScan, but again, this dbScan code is being showed you for a random sample. So I'm using the same random sample, which we created over here, the 3 clusters. And therefore, when you see, I'm getting it over here. And you can see that these are my core points, while the black points are my border points. So you can clearly see that what you're playing around with in dbScan are 2 parameters. One is what is called epsilon, that means the radius around the star. And the second thing is what is called the minimum number of points. That means I'm looking for every point within an epsilon radius. Do I have my minimum number of stars? So these are the 2 values you're going to play with, 0.6 and 5. You'll see that if I, for example, reduce the value of epsilon, that means I'm going to take a very small radius around a star, and I'm saying I want 5. So you'll see that obviously it will not be able to identify. So if you see over here, it's going to identify very small clusters because I'm giving it a very small epsilon radius. On the other hand, if epsilon is very large, for example, it is 8.8, okay, then you can see it may, okay, that's good enough, it's working well over here. But if, for example, if epsilon, let me make it 2.8, this is just for fun. I may do this and okay, it's still working out well. It's giving me this thing, but for example, if let me make it say 5.8, then it may even do something as dangerous as joining 2 clusters, right? I'm just going to make it very big. I'll make it 15.8. And you can see now all 3 of these are put in as 1 because your epsilon radius has become 15.8. Right? So when you're using machine learning tools, you have to be very careful about what are the values of these parameters you are taking, right? Like I told you for k-means, what is the k value? In dbScan, the important criteria is how do you choose your epsilon and how do you choose your minimum points, right? What is the number you should have? Say 5, 10, 20, 15. what is the number, and that's the crucial bit. In the paper which I had referred to you, there is an explanation given on how do we actually choose our epsilon and minimum points. You were also showed classification, right? So I will not run this in too much detail, but for example, you can actually see how can you use random forest, for example, to do star galaxy separation. Because what happens is, for example, you have a catalog of a certain part of the sky. You don't know which of them are stars and which ones are this thing. So we can actually use, for example, random forest to classify. This thing. I've even given you all code over here, which you can run later on and use this to actually define. But what the generated code, the problem in this is that all stars are 0 and all galaxies are 1. So I have a sample of 5,000 objects, of which half are stars and half are galaxies, which you can see over here. I then train it like we did it for random forest. I do training. I've taken it with a 70-30. So you can see test size is 0.3. So one is 3,500, one is 1,500. An important thing I forgot to mention to you is that when we run these codes, you have to always scale your data, okay? Because, for example, it could be that your, all your features which you have, they will have a different range, right? Your feature could be your distance to the star. It could be the velocity of the star. All of them are going to have a different range. And therefore, what we do is we generally scale all these things so that all of them are within, say, a range of, say, 0 and 1, for example. Because otherwise, if you have large values for one value, then that thing is going to dominate more than the other quantities. And we don't want that to happen, because for every object, we have certain features. And we want equal weight to be given to all the features. So we scale it. So here you can see there's a feature scaling thing. We scale the thing before we run the code. And then we run the code over here. This one is given a perfect example because we have pure stars and galaxies in this thing. I'm sorry I'm running out of time, but I will try to end fast. So you can have a look at this code and do it. There's another one for supernova classification. As part of this thing, I've even put one for regression in astronomy. So for example, if you're doing linear regression, here is the code for it. We've put some random set, which is X, giving you 100 points, which are with 5 magnitude, right? While Y is the one which is giving you the redshift, which is 0.5 into X, the random number, plus with some noise element, because you want a scatter, right? Otherwise, I would have a perfect line fit. I'm plotting my X and Y, and I fit it to, because you can see that I've done a fit of linear regression, which is XY, and I've done it like this. If I look at this data and I don't think it fits a line very well, I can even fit it to polynomials. So I can even do a polymodel fit, right? And accordingly fit it to a polynomial, right? And get it like that. So here in the end, there's a list of assignments. You can try doing it. For example, you could try K-means clustering for a SDSS data set, try accessing the data set, look for it. You can even do classification for this, for something. You could do redshift prediction with regression modeling. So there are a few examples given over here. And please try to go through these things and see if you can find something interesting to do. So I hope I've given you a good number of options for your capstone project. Either the star cluster thing is there, as well as these assignments which I've listed over here, and you can use it. I'm sorry, but now we only have 4 minutes for questions, but please do your questions.
SVMB.
Yeah, the file also has on vector machines, SVMs, so you can have a look at that too. And yeah, so Anjana Shri wants to know what kind of capstone projects can be done with exoplanets. So I should not be doing this, but if I promote my own YouTube channel, there are some ways in which you can actually use Kepler data and use that to analyze it to get exoplanet data. So what can be done is you can use Kepler data. You decide on whether you want to do it in a supervised method or unsupervised method. If you're using supervised method, then you maybe have data for some of the exoplanets for which the parameters are there. You provide that with the training data set, and then you use that to find out the parameters for unknown light curves, right? So try to look for some papers. I think a good idea, if like for example, if you're looking for exoplanets, a good idea would be, for example, to I'll just show it to you. For example, machine learning. Can you just this thing? Can you just unshare for a minute? Yeah. Yeah. So for example, just a minute. The simplest way, which I did, was I just Googled it. So you can see identifying exoplanets with machine learning methods, a preliminary study. You can look for this paper, or you can look for, when I Googled it, you'll find a whole bunch of other papers, deep learning methods, etc. So you can actually have a look at any of these different sources. Either these are these are video lectures, or there are papers where you can go through how machine learning has been used for planet detection. Okay, thank you. Yeah, now what do you want to do? Your time is up.
I just wanted to share this notebook has been shared with you, where you use this support vector machines, SVMs, and this is used for classifications when you have various variables, right? If it's not independent variable and dependent, they are just two, but they can be many. So this is a notebook you can go through, and this is used for classification of supernovae. And so supernovae, the peak brightness is important in different magnitudes, U, G, R, I, and Z. Decline rates are important. The color, which Daniel spoke about, G minus R, I minus Z, these are important. The spectral line strength, whether it's silicon absorption lines are present or not, H alpha is there. So that defines whether it's uh, um, 1A supernova or not. So here you can go through this. And like Priya mentioned, the data has to be normalized. Otherwise, you have issues with it. And if you go through this notebook, you will see how is the work flows through it, and what are the advantages and disadvantages. Advantages of SVM for high dimensionality, it works very well. It's a very robust one, and non-linearity also uh, uh, gets captured very well. So these SVM models are extremely good. So here we are looking at some generated data, but you can also use actual data and do it. And here is the one where you set it up, use the uh, you know, Scikit-learn and load the data, and you do it, and you are classifying it. And this notebook shows you for different wavebands, different things. Where is it peaking? What are the averages? And so you go through this. There are notes in it which will tell you, and the confusion matrix tells you how good the models are in fitting it. And this is a very important thing which gives you a tabular representation of the performance of the classification models. So maybe we'll stop with this because we are running out of time. And if required, we can continue in our next session.
All right, thanks.
Then,
Just to
Yeah.
help us prepare for our next session, since everybody's on Slack, do send us messages if you want us to focus on a particular topic in machine learning, because next week also we'll be doing machine learning. So please you let us know if you want a specific topic to be handled. Yeah, thank you.
All right, thank you, everyone. Thanks for joining us this morning for the section, and then we'll also reconvene in the evening for those who did not make it this morning. So it's actually the same information shared this morning that will be shared in the evening. So please take your time and walk through your notebooks Again, I've seen a couple of questions asking about Capstone. Please, you want you to collect your data, do your analysis, write everything you want. You can actually make presentation in your notebook. You can make your presentation in your notebook, add images, add plots, make the plot, we can see the plots, write description, the same way it's done in the notebook, all in Colab and share it. We don't have any more time. The submission link will be shared later this week, probably tomorrow or next. And we expect that submission will start kicking in if you're done with it. So please kickstart your project and do not wait for anybody because there's no time anymore. Also, I'm seeing somebody saying, what possible analysis can be done on astrometric data set? I'm not so much. So it could be, you have to probably check parallax, astrometric positions, parallax proper motions. Those are the key things that crosses my head. I'm not so sure, but it could be, because this is probably positioning. It's more like your positioning and distance related and their motions in the sky. Yeah, maybe things like proper motion, moving groups and the rest of them. These are some of the things that you can do. Proper motion of stars, whether objects are high proper motion, are they young stars? I think I'm not so sure. You can look at things around the tangential velocity. Yeah, you say you may have to do a bit of derivation. That seems like looking at the tangential velocity to understand their kinematics, but this is not I can give you all of that off head now, but I believe that a little digging will help you figure that out for machine learning. But again, we've come past time. Thank you for joining us this morning. Please, we've been sharing resources with you. You can only learn better, just like we've told you in machine learning, when you expose yourself to the resources that have been shared with you, from the slides to the notebooks. Get your hands dirty, run them, read them, practice them, test them, check online. You will see other things. If you are confused about certain things, ask questions. You can also search online. These are the many ways you can use to get yourself started and understand the topics better. So thank you again for joining us today, and then we'll see you next week. And we're also looking forward to your project submission. Bye, everyone.
Bye.